बिस्मिल्लाहिर्रहमानिर्रहीम। इसके अंदर मैं एरिया मेथड से रिलेटेड जो कन्फ्यूजन है वो दूर करना चाहता हूँ इस वीडियो के अंदर। ये आपको वही प्रॉब्लम है जो हमने क्लास में डिस्कस की है। ये ए से लेके डी एक बीम है, एक बीम सिंपली सपोर्टेड, और इस पर यह कि यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड है 20 फुट तक, 2 किप पर फुट, और फिर ये 10 फुट के ऊपर यानी यहाँ पर एक 10 किप का लोड लग रहा है। इस ये एरिया मेथड में हम जो फर्स्ट पॉइंट है जहाँ से हमने स्टार्ट करना है शेयर फोर्स हो या बेंडिंग डायग्राम हो, वहाँ पे हमें ऑर्डिनेट पता होना चाहिए। मसलन अगर ये 32.5 के प्रोजेक्शन है तो हमें पता है कि यहाँ पे जो शेयर फोर्स है वो -32.5 किप है एज़ पर आवर साइन कन्वेंशन। तो यहाँ से हमने स्टार्ट लिया, ये हमारा स्टार्टिंग पॉइंट है, ठीक है, इट्स आवर स्टार्टिंग पॉइंट। ये स्टार्टिंग पॉइंट यहाँ से हमने शुरू किया, और फिर उसके बाद नेक्स्ट किसी भी पॉइंट पे मसलन बी पॉइंट पे हम अगर फाइंड करना चाहें कि शेयर फोर्स की वैल्यू कितनी है, वैसे तो हम किसी भी और पॉइंट पे कर सकते थे, लेकिन चूंकि वही ट्रेंड कंटिन्यू करेगा अप टू पॉइंट बी, इसलिए हम पॉइंट बी के ऊपर देखना चाहते हैं कि शेयर फोर्स कितनी होगी। तो उसके लिए हमारे पास ये रिलेशनशिप है, V2 इक्वल टू V1 प्लस एरिया बिटवीन एरिया अंडर द लोड डायग्राम बिटवीन x1 एंड x2। लेट्स सी हमारा x1 है 0, x2 हमारा ये 20 फीट। So area between these 2 points A and B is 2 the intensity of the load, uniform intensity, multiplied by 20. So 2 multiplied by 20. This is the area. So V1, and we are taking downward load positive, so it means this will be a positive area. So V1, which was -32.5, plus area under the load diagram between A and B, which is 2 into 20, 40. So I would say the shear force at point B at this location, the shear force would be, let me just show you the calculation, -32.5 plus, I'm just applying this formula, plus the area between points A and B, which was 20 into 2. This was the area. It's a positive area because we consider downward load positive in our derivation. So the result is 7.5. Let's say this is the shear force. That's why I'm saying this is the shear force at point B, 7.5. I'm removing this. I just want to remove it because I don't want to confuse you with. So this is, this is how we completed this step. And how should we join these 2 points, -32.5 and plus 7.5? This is plus 7.5. How should we join them? Should we join them by a straight line, by a second degree line, or by third degree line? If this is a 0 degree line, load is a 0 degree line, then you know that this will be a first degree line or a straight line joining these 2 points. So, and you know that the point where shear force goes to 0, the bending moment at the same point goes to maximum. So we need to see where exactly this zero shear point occurs. So we need to locate its position on the the point where shear force goes to 0. So we need to consider similarity of triangles between this red triangle, this triangle and this triangle. So similarity between them, we should be able to look at this. You should be able to find x, the distance of that 0 point shear from the left end. So we come to know this is 16.25. So this is at 16.25 from the left, this is the point where shear force goes to 0. All right, let's move on to the next point. Now you can see that in order to, since there is no load between B point and just to the left of C, we don't see any load, so this will continue straight up to this point, and then just to the left of C, the shear force remains still equal to 7.5 kip, and then when you just go beyond point C, just to the right of C, there is a jump in shear force diagram equal to P load itself. So V positive phase minus V negative phase equal to P. We have discussed this before. So if you want to find the V positive phase, you take this term on the right side. So this becomes V positive phase equal to V negative phase plus P. So this is how you can calculate. So that means this will be 7.5 V positive phase, let me write the expressions for you. So V positive phase just before point C, just before point C, just to the right, just to the left of C, the shear force is 7.5 kip. Sorry, V negative, this is the V negative phase value, okay. And we need to find V positive phase, which is just to the right of C, and this is equal to V negative phase plus P, where P is taken downward positive. So if you put these values, 7.5 kip plus P, 10 kip, it is downward, so we consider it positive. So now you see that this will become 17.5 kip. So this is how we calculate the change in shear force between, so as we encountered a concentrated load. So this was 7.5 kip, and then now this is 17.5 kip, as you can see over here. So this is how we calculated these things. And then let me remove this. We're done with this. All right, and now once you are just to the right of C, your shear force goes to 17.5, and then it continues at that value because there's no load encountered between C and D. So it continues 17.5 just to the left of D, and if you like to say it that way, you can say it goes down to 0, but this is what the value, shouldn't say goes down to 0, but this is what the value at the end is, 17.5 kip. So the shear force diagram is complete. You can confirm that this value is the same as the reaction over here. So this is confirmation of the confirmation that the shear force diagram has been correctly plotted. And then drawing bending moment diagram, you will need to look at the shear force diagram, because this is the relationship between the bending moments at two sections. So the bending moment at section 2 is equal to bending moment at the previous section minus the area of the shear force diagram, area under the shear force diagram between those 2 points, x1 and x2. So for that, again, we need to know the bending moment at the starting point, which is 0 in this case, because there is no moment, there's no reaction over here, moment reaction over here, no applied moment, so there's 0. We see a 0 moment over here starting from 0, and then the change will take place as we go along the span of the beam. We are interested in the new value in finding the new value of the bending moment at this point. I mean, you see this is a straight line going on, so you calculate the bending moment at the point where shear force goes to 0. For that, you need to know the area between these 2 points where you want to find a change in bending moment. So these are the 2 points we are considering, this point and the point where bending moment, where the shear force goes to 0. So you need to calculate the area under the shear force diagram between these 2 points. Since it's a triangle, so it's quickly calculated is half. You can see half over here, base into altitude, or whatever you like to say, one dimension into the dimension. So this dimension is minus 32.5. So then you will get minus 264.4. This is the area of the area under the shear force diagram between point 1 and point 2. So the shear force at point 2, at this point, the bending moment at this point where shear force goes to 0, at this point, it is, you calculate it like this. I mean, you know that M2, look at this formula. I'm just using this formula. M2 is equal to M1 minus area under the shear force diagram between x1 and x2. I mean, you can write it whatever way you like. So M1 in this case is 0, the bending moment at the previous section over here, and the area between x1 and x2, we just calculated it is minus 264. So this is how you put it over here, and then you see that the answer would finally be plus 264.4 kip foot, whatever the units are. So 264.4, I'm guessing this should be the answer, 264.4. So that's how you come to know the value of the bending moment at the point where shear force goes to 0 at any, I mean, so this is the value now, 264.4 at this location, and you would now like to know the bending moment at the next location, which is this point B. So in order to know the value of bending moment at this location, knowing the value of the bending moment at this location, so again this time M1 is the previous value of the bending moment would be 264.4, and we want to calculate M2 again. So M1 plus area under the shear force diagram between those 2 points. So this time you can see M1 is, you see, I'm sorry, there is a negative sign over here. I mean, mistakenly I wrote positive sign, but it's a negative sign over here. So M1 is now 264.4. Oh, you see, M1 and M2 are so for this case, you know the value at this location. So this is where M1 is, and this is M2. This is what you want to find. So M2 is the previous value of the bending moment, which was 264.4, and then the change in bending moment is equal to the area under the shear force diagram. So that area you can calculate again from here, which the area would be half into 3.75, this dimension, and this dimension is 7.5. I shouldn't say dimension or whatever you want to like it, whatever you like to call it, but this would the, this is how you calculate these things. So 14.06 is the area between these 2 points, 14.06. So now using this area, so how you minus, so 14.06. So you will calculate this to be, 264.4. I'm just calculating on my calculator, and I can see that this value is about 250.3. So 250.3. This is how you get the bending moment. Now again, let me tell you why I joined these 2 points, the previous two, the value between these two, this point and this point, why I joined them by a second degree line and not a straight line is because this was a first degree line. So the bending, shear force diagram is a first degree line between these 2 points. So this must be a second degree line, one more than the previous. So it had to be like that. And why should I join it this way? And not this way. Why should I not do this? Because you know that the shear force at this point is 0, and that means the bending moment diagram should have a 0 slope at this point. And this is only possible if I draw it like this. I cannot get a 0 slope if I start drawing this shape. So this is why I'm drawing it this way instead of this way. Okay, so, and similarly, why should I join them by straight line? Why should I join them by, again, this is also second degree line, this also second degree. So why should I join by second degree line? Because this is the first degree line shear force between these 2 points, so it must be a second degree line. Again, the same reason. And why should I join by the way I have joined? Because this is the only way I can join them, satisfying the slopes. If this is the shear force at this location is 0, the bending moment diagram slope must also be 0, and this is the only way I can join them. And then from this point onward, you can see, the bending moment at this location. Now use this value 250.3 minus again the area between this point and this point, area of the shear force diagram between these 2 points. So again, this area is 7.5 multiplied by 10. So you get about 175. See? So this is how you, and now you should join them by straight line, because this line is a 0 degree line, so this must be a first degree line, which means should be a straight line. And then again, from this point onward, you would say 175 minus the area between this point and this point, area under the shear force diagram. So that area is, again 17.5 into 10, and this happens to be 0. Okay, and the previous value was about 175. This is 0. So this is why you are here. And again, this is 0 degree line, this one. So this must be a first degree line, and this is why you have joined by a straight line, this straight line. So this is how you complete the bending moment diagram. So in area method, you draw the shear force diagram by looking at the area diagram, and then you complete the bending moment diagram by looking at the shear force diagram.